Okay. So let's talk about compounds and how elements combine to make various different compounds. This is also going to be where we start talking about like naming. So we will have a bit in here that's sort of the learning the language of science. Please like make sure you actually try to learn that and practice that. Okay. It's like any other language course or learning a language, you got to use it. Okay. So one of the key rules I need to sort of talk about, and I hate the naming for this. I think it's a terrible way to name this because it really makes things harder for you later. Okay. Okay. So your book is going to call it the octet rule. Okay. Octet meaning eight, right? Okay. So what they're referring to is that the main group compounds typically want to have eight electrons. Okay. So if you look at periods 2 and 3, the number of electrons those things want is typically 8 electrons. Okay, and they all try to get 8 electrons overall. Okay. All right, I'm going to give you a slightly different rule for that, and that's that everything wants to be a noble. Okay, everything wants to be like a noble gas. Everybody know where the noble gases are? Okay, they're that last group, right? On the far right. Now, notice that we have the atomic numbers going up. Everybody say okay? So all things being equal, that's the same numbers of electrons, isn't it? Right? So what you'll notice here is that you can go left, can't you? If you had a lithium, it could lose electron to be like helium, couldn't it? And if you're on the right side, you can go right and gain electrons. And that's going to be, then if you have fluorine, it gains electron. It's going to be like neon. Okay? Okay, so let's go ahead and talk about this a bit. So when you're looking at these, remember that it's the electrons arrangements in the atoms that's going to be more stable when you combine elements or you gain and lose these electrons. When you're all the way to the right of the periodic table, when you're noble-like, you have filled up all the spots that are available for those electrons. Okay? The exact location of any given electron outside a nucleus is incredibly difficult to determine. They're very light, they're very small, they pop in and out of existence. They're basically impossible to actually nail down. Okay? It's kind of like nailing down a specific person's position within a city. It's actually pretty difficult too, right? And so that's why we usually refer to cities with an area, right? So New York City, it's an area, right? We don't usually talk about like finding Bob in New York. Okay. Very difficult to do, right? So in the case of electrons, we're going to find the areas that they are going to be in. And those are going to be usually referred to as an electron cloud, but also orbitals, shells. Okay. And again, remember they're the area you're going to find those electrons in. Typically 90% of the time is the limitation we set. Okay. All right, so electrons are going to be charged. They're going to be in constant motion. They possess energy because of these things. And they actually possess an inherent amount of energy beyond that. And so they're always energized and they possess an energy. Okay? And so we're going to refer to these positions of those electrons by their energies, actually. Right? You see those... we go over into these rows on the periodic table. They're called periods, right? Okay. They actually have other names as well. Okay. They're called periods, but they're also called energy levels. And you can also call them shells. Okay. All those names are true. They're also called principal quantum numbers, but you guys are not going to need that particularly. Okay. If you decide to go further in chemistry ever, you'll want that. All right. So remember, especially like the shells and energy levels part. Okay. When you're looking at the periodic table, you're actually looking at sort of a distance map from your nucleus. Okay. As we go down the periodic table, we're actually getting out further and further from your nucleus. Okay. So electrons are going to only occupy certain energy levels. You can think of it a bit like a staircase. They can't occupy in between or else they just fall down. Okay. In general, the electrons will occupy the lowest energy level first, You can think of the energy levels as being a bit like the floors of a building. If we don't have the floor below us, what are we going to do? We're going to fall down, aren't we? Okay. And that's the same thing for the electrons with the nucleus, right? If there's nothing blocking it, it's going to head towards the nucleus because they're attracted to each other. Okay. And so what blocks it from heading towards the nucleus is other electrons, right? As you put electrons around the nucleus, they'll block more electrons from coming in. Okay. The lowest energy level is going to be found closest to the nucleus. Now, the staircase analogy breaks a little bit in the fact that usually stairs are even. And it's the same distance per stair, right? In our staircase here, these stairs are not going to be even. What's going to happen is as we go up the stairs are actually going to shrink. Okay? The stairs are going to get smaller and smaller. Right? Basically, it's less distance each time you go up. Can everybody see it okay? Okay. And you can kind of know this already. I mean, sort of think about it. We're going the distance from a nucleus, right? That's actually how gravity also works. You get pulled less by gravity the further up you go, right? So you kind of knew this, but maybe not as much. Same thing happens with a magnet, right? Everybody's played with magnets before, brought them together, and there's like a distance where it barely pulls, right? Then you go further, it pulls more. You go further, it pulls more. And eventually it gets really strong and like slips together on you, right? Because it kind of shocks you. Okay? Same thing's happening here. Remember, this is negative and a positive charge being attracted to each other. Okay, notice these are the N numbers. That's principal quantum number or energy levels. These are the shells I was talking about. Also the periods of the periodic table. Same thing that's being created here. This is energy as you go up. And so as you go up, it takes more and more energy. Think of it like this. If you're at the top of a 10-story building and you hit the ground, you're going to have a whole lot of energy to release, right? Top of the 1-story building, not a lot of energy to release, do you? Okay. Ground floor, almost no energy to release. Maybe a little bit in this case because we're a little above the ground and ground floor, aren't we? Yeah. Okay. Anybody have any questions about that so far? Fantastic. Okay. So the maximum number of electrons that can be found in any given energy level actually can be calculated with this formula. It's 2n to the second power. So at energy level 1, which is the first energy level we fill stuff up with, we're only going to have 2 electrons that can be put in there. Hey, look at that periodic table real quickly. How many elements are on the first period? 2. There's hydrogen and helium, isn't there? That's the same number as this, isn't it? Why can you fit only 2 elements on the first period? Because there's only space for 2 electrons. That periodic table is actually structured based on these rules here. Okay? That's what you're seeing. And so if you ever forget these rules, guess what will tell you these rules? The periodic table, which I always give you on exams, won't it? So how many electrons can fit on the first period? 2. You know that from? Periodic table right there, right? Okay. We go down to the next period, next energy level, and that is 2 to the second power, 4, times 2, which is 8. And anybody remember I said octet at the beginning of this? 8 electrons? Yeah. Period 2 has how many elements on it? 8 again, right? And that's literally what we're seeing is on period 2, you can only fill in 8 electrons. So you can only have 8 elements filling 1 electron in each, right? You're gaining 1 electron each time. And so that's actually what you're looking at again. We go to the next period because our energy level, our period is full when we're at the noble gases, right? And so you have to go to the next one to put any more electrons in. Okay? Okay, now period 3 is where things get a little kind of weird, all right? And so period 3, we would have 3 to the second power, which is 9, right? Times 2 is 18. There is not 18 elements up there, is there? No. Okay, so this room is a fairly decent example. You may notice there's spots in this room that don't tend to get anybody sitting in them. Why don't people tend to sit in those spots? They're uncomfortable, aren't they? Okay? They're kind of awkward positions in the room, so people don't want to sit there, right? The same thing actually happens with electrons to some degree. These are positions as we go out that become kind of weird and uncomfortable, okay? So I'm going to kind of draw this out. Here we have a nucleus. It's way too big, okay? But you won't be able to see if I drew it on the correct size. And right there, we would have energy level 1, okay? And this would look like energy level 2. And this would be like energy level 3. No Picasso in my eye. Okay. Now, as we go out, what you're going to see is this is going to be filled, right? And then we go out and we have more space. And so that's why we can only put 2 electrons here, because there's very little space. As we go out, we can put 8 electrons, so a lot more space, right? Okay. And we can fit 18 electrons into here. But what ends up happening is once you start putting these electrons in, they repel each other, right? And so what ends up happening is when you try to fit that last remaining 10 electrons, they're actually really high energy. And so what ends up happening is you actually go to period 4, and it's actually more energetically efficient to start just putting electrons in there, okay? And on period 4 is when you actually fill in those 10 electron spots from period 3. And that's why there's 18 again, okay? And so those extra 10 spots, that extra accommodation for 10 electrons on period 3, doesn't actually get used until period 4. Okay? That's also why you're going to see there's like weird behaviors that you can find for period 3. Okay? For example, if you look at phosphorus and sulfur, they can actually make more bonds than you'd expect them to make. And that's because in reality, they have extra spots put on it. Okay? So they can do some kind of fun and weird stuff. All right. The same thing actually happens on period 4. You should actually have more electron spots. They don't get used until period 6. And that's why you have that little insert that comes in at period 6. That's actually using those really bizarre spots on period 4 to fill those in. They're just so weird and awkward that they don't get filled in until then. Okay? Okay. Think of it a bit like, has anybody ever seen where they take a magnet and they put it like in a pit of iron filings and it makes these weird designs? Like radial designs? Okay. That's actually what these magnetic fields look like. And so if you ever look at those, you'll see there's like little spots that are kind of whirly. Those are the higher energy spots. And that's actually what we were talking about here. But you don't need to know it to that degree. You just kind of have to go, okay, yeah, sure. 8 electrons on periods 2 and 3. And how do you know that? Well, you really just have to look at the periodic table, don't you? Yeah. So how many electrons does it want to fill up on period 2? Count across from left to right. There's 8 spots. It wants to fill in 8 electrons. Okay. That would be a full octet on period 2. 8 electrons filled in, full octet on period 3, right?
And 4 and 5 have 18.
Mm-hmm.
And then 6 is 32.
You got it.
Just 7 have.
Same.
32.
Mm-hmm.
Is that where it stops? We only have 7
right
periods?
now. Yeah, right now it stops there. And realistically speaking, we probably will never actually be able to test like what those next set of orbitals look like that were made on period 5. But like there's theoretical models of what they'd look like. Mm-hmm. But the stuff we've been making at the end of period 7 doesn't last long enough to get electrons on it. So, yeah. It just blows itself up. So what are you going to do, right? Yeah. All right. So anyways, these are some different examples of different elements and their numbers of electrons on each energy level and which energy levels they have filled in. Okay, So being able to locate the number of electrons present in each energy level is going to provide insight into how the elements in a period of or group are related to each other. Note that as we go down a group, we actually have the same number of electrons on that outer shell each time. That's actually what the group numbers are referring to. So elements in the same group on the periodic table have the same sort of structure on the outside, the last energy level, the outermost one. Okay? And that's what makes them have similar chemical properties. Because what would you interact with when you're interacting with your computer? Do you interact with the keys on the surface, or do you reach down inside and change things? Keys on the surface, right? You can't reach inside, can we? And so when we have a atom, the electrons you can interact with are always the ones on the surface, right? You can't get past these ones on the outside to really mess with this stuff, right? Okay. And so you see boron here and aluminum. This is group 3A. And so they're going to have 3 electrons and their highest energy level. Now, these groups work really well for those first 3 periods, specifically periods 2 and 3, okay? And those are typically what's called the main group elements. And realistically speaking, we're looking at like 90-something% of the mass in the solar system at that point. So most chemistry situations you're going to see would be those, okay? All right, so let's talk a little bit more about the terminology. So the highest energy level that contains electrons is going to be called the valence shell. It's the energy level that's furthest out that has electrons in it, okay? The electrons in that are called the valence electrons. Literally, they're the electrons on the outside of an atom, okay? The valence electrons are going to be furthest from the nucleus. So whatever electrons are in the outermost energy level, outermost period, those are valence electrons. Whatever energy level is filled in last, the furthest out energy level, is the valence shell. Okay? So these electrons will combine when elements make compounds, because they're the ones on the outside that are going to get moved around, they're going to get stolen, they're going to be added to, they're going to be shared. Okay? Okay, the groups and columns indicate the numbers of valence electrons in atoms, at least for the main group elements. That's that 1, 2, 3, 4, 5, 6, 7, 8 with an A behind it. Okay? It makes it faster for you to do this. And that's why they have that numbering system. The periods are going to indicate the outermost energy level containing electrons. Again, that's that valence shell again. Okay? This is how that works out. And you can see that on my little periodic table here. I've been demoing it on that periodic table up there, right? Okay. Did I lose anybody there? Oh, okay, fantastic. Okay, so elements in group 8A, or these are going to be the noble or inert gases. They're going to be on-reactive in all but the most extreme conditions, and that's because they're full, aren't they? If you try to add anything else to them, it would have to go up to the next period, wouldn't it? The next orbital, the next group. Okay, so you'd actually have to add to a whole new energy level. It's a whole deal out, right? And so when you look at the noble gases, they're full. They're not going to be very on-reactive. Typically, you're not going to see reactions. Again, the noble gases are typically said to have a full octet. And so again, that's going to be neon and argon we're talking about, where they'll have 8 electrons and they're full. Okay. Okay, notice that helium is only going to have 2 electrons because it's going to only fit 2, right? But it's full at 2 because you can only fit 2 in period 1. Right. Now, again, that's where the octet rule comes from. That has a full valence shell, which is 8 electrons for your main group. Now, let's try to come up with how we're going to do this in the future. If we look at, say, fluorine, how many electrons does it want? So we look up at F. And how many is it over from the noble gas? It's 1 over, right? And so typically fluorine is going to gain 1 electron which would make it F minus, negatively charged. Okay? And the reason it wants to do that is that will fill in that energy level 1. And so they would have a complete full energy level. Okay? If we look up at oxygen, how many does it want? 2. We just count over, right? Okay? And so typically 2 minus. Nitrogen, 3. And so that would be 3 minus, right? We go over to carbon, 4. And so that'll typically gain 4 electrons. Though carbon's an interesting one because what would happen if we go the other way? Go left. How many spots is that to get to an open? So we go to B, boron, right? We go over to Be, 2, Li, 3, He, 4. And so that's again 4 steps for carbon. So carbon's an interesting one that I can kind of do both. Okay. Boron. You're tempted to go to the right, aren't you? Yeah. But it's faster to go left. So boron typically uses 3 electrons. It only has 3 electrons it can give to things. And it typically goes more to the left. Okay?
Meaning it wants to give away its electrons?
Mm-hmm. You got it. And so aluminum does that all the time. Aluminum always loses 3 electrons and has a 3+ charge.
Does this relate to electronegativity?
It does.
So the closer we get to fluorine, the greater our electronegativity
is. Yeah.
But boron wants to give away its 3 rather than accumulate 5.
Yes.
So does that make it more, like, what's its electronegativity?
So boron is kind of an interesting case, and that's why it sometimes is metalloid, sometimes it isn't. Yeah. And what ends up happening with boron is it kind of wants to give its electrons away, and it typically makes 3 bonds. But more often than not, it's going to use what's called covalent bonding, which we'll get to in a second. Yeah. And it'll actually share the electrons rather than losing them completely. Yeah. And it can make some really weird and crazy stuff. Okay, so let's talk about ions. So if we have an atom and it has gained or lost electrons, then we're going to have an unequal charge, right? And so if we have a fluorine, it gains 1 electron. We're going to have a negative charge. This is going to be called a fluorine atom, or otherwise known as fluoride, which we'll talk about the naming in a second. If it's negatively charged, we're going to have an anion. If it's positively charged, it's going to be a cation. That means it's lost an electron. Okay? Okay, so again, if we gain electrons, negative charge, anion. If we lose electrons, positive charge, cation. Easy way to remember that is cats are positive, ants are negative. Okay? Okay. So, cats are positive, cation, ants are negative, anion. Okay, so the elements all want to go to the nearest noble gas. When they have the same electronic configuration as something, we call this isoelectronic. And so they want to become isoelectronic with that noble gas. Okay? They want the same electron configuration as that noble gas.
Because they just want stability.
Exactly. They want full stable orbitals. Okay, and so this is the trends of the ion formation. You're going to notice that directly is the same sort of trend as you see in the groups. Okay, that's actually one of the reasons the group numbers are the way they are, is it just makes it faster to do that. Okay, there's something I actually have to mention before we get into this in a great deal of detail, is number 1, see the transition metals in the middle? That little thing that goes down in the bottom? This part here. Those are called transition metals. Okay? And what you're going to see with those is they actually can have multiple different charge states. Okay? You can have a chromium 2+, a chromium 3+, and even a chromium 6+. Okay? That's a little bit rare. And that's actually referred to as hexachromium. Chromium 2+ and 3+ can be nutrients. Chromium 3+, if I remember correctly, is the one your body actually uses. Chromium 6 plus is a very toxic substance that will cause chaos in your body and give you all sorts of different leukemias, cancers, everything else. Yeah, really, really nasty. Okay. And so polyatomic ions, did I ever tell you guys about Aaron Brockovich? You guys ever heard of Aaron Brockovich?
Yes, I saw her movie.
Yeah. So there's a pretty good movie. Has Julia Roberts in it. It is semi-accurate-ish. Based on a true story, that sort of thing. But if you ever get a chance, watch the movie, I guess. So Erin Brockovich was paralegal. She worked for a lawyer. And what ends up happening is there was a chemical company that released hexachromium into people's water. And they knew they did it. And so what they did is they brought the town together and said, hey, we released chromium into your water, and told them it was the chromium you need in your diet. And so no problems. It's something you need in your diet anyways. No issue. About 400 medical procedure people went to the hospital and died later. The people, some of the people became convinced it was because of this company that was leaking stuff into their water. And so they tried to find a lawyer to fight this. They finally stumbled on Erin Brockovich and the lawyer she worked for. She looked it up and found out that they had told these people that was a healthy form of chromium, but it was actually hexachromium that they leaked into the water. And the reason they told these people that is because there's a statute of limitations when it comes down to these things. They were about 4 years away from that statute of limitations expiring, and that company would have been legally not liable anymore for killing hundreds of people. So, anyways, they sued, they won. That company had to pay out damages for medical procedures, etc. Probably people should have went to jail for it, but they did not. One of the interesting things also to this is the lawyer in that Erin Brockovich case, big hero that day. A couple of years ago, he actually was found to be embezzling from his clients. And so I don't believe he embezzled in that case, but you can be a hero one day and a villain the next, right? So, anyways, interesting little thing. We'll start up on well, we have 2 more minutes, guys. So we'll do the rest of 2 minutes. But polyatomic ions, this is going to be consistent of a group of nonmetals. They're going to form ions. You may have noticed that I mentioned covalent bonds before. These are actually formed using covalent bonds. And we'll get to those in just a second, but I need ions first. Okay. So note that they're nonmetals that will be bonded together, and then they have an overall charge. That's polyatomic ions. Now, one of the things you may have noticed that when I was talking about ions, I kept talking about metals and nonmetals like they're separate things. And that's because they're separate things. And so ionic compounds tend to be made of a metal and a nonmetal. Okay? So metals and nonmetals typically make ionic compounds. Now, this right here is the charges you'll typically see. Anybody notice that those are the same charges I was discussing before, isn't it? Okay? I made you guys figure this out on your own. So you don't need me to tell you everything. You have logic. All right. And so, for example, how do I figure out, well, fluorine usually wants 1 electron. Well, I look at my periodic table, I go over 1, right? So to be isoelectronic with a noble gas, they typically want to gain 1 electron. Okay? Oxygen's 2, nitrogen, phosphorus, 3. You'll notice that these ones are actually dropped because they do some interesting chemistry. For example, carbon can do either way, right? Aluminum typically wants to lose 3 electrons. These are transition metals. These ones 1, these ones 2 electrons. Lithium's unique. It can actually make covalent bonds, so that's something interesting about it. Okay, these right here are polyatomic ions. Look at those. You want to semi-memorize those. You want to have those down well enough that you know which ones are polyatomic ions and sort of the charges on them and be able to name them to some degree. You'll mostly get those memorized just from homework. Okay? Okay, you all have a wonderful day. We'll start up here next time. look at those polyatomic ions, get some experience with them.
There you go. Now you can't forget. You're
Thank you.
Get yourself a try right
Thank you
now.
very much. Okay. Yeah, that will be a. You can definitely get it done. Oh yeah. Oh yeah. The lab takes like about an hour if you're quick about it. Oh, okay. Do you have a pen or something? And then when I get around to putting my attendance in, I can put you in.
Thank you so much.
No problem. Thanks.
Yeah, so like the QR, like what is that? Like at the beginning.
Oh, okay. So that's Plicker. Okay, put your name down first,
Okay.
so I can put my you in my attendance. Okay.
Okay.
But what you want to do is
I think it gives me a really great overview. Of
I think you were on my list whenever I started. If you're not on my list, let me know. Okay.
Okay.
And so under assignments on Canvas, so under Canvas assignments, there's an assignment towards the end. That'll be Plicker.
Okay.
And under Plicker, there's a list of people versus numbers, and then there's a list of the numbers, which are the QR codes. Yeah. And what you can do is you can like print that off onto like your phone or computer or whatever, or print it off on a piece of paper and put like the front of your book thing. And what you do is you hold it up, and here, I'll do the example with this, but it's not the same thing. So like you'll have your 30 or whatever will be your part. Okay. And it will have an A, B, C, D. And so you'll be like, I want to answer A. If I want to answer B.
Oh, okay, that makes sense.
Did that make?
Okay, so I just have to print it out and then.
Yes, indeed.
Okay.
Yep. And you can do it on your phone or computer too. You saw some people were doing it like that. It is recommended you keep like a copy on a digital device in case you forget.
Right. Well, thank you.
Most definitely. You take care, okay?
I was just wondering on the Pearson assignments, the pre-lecture and post-lecture, can you still turn that in late?
You can.
Oh, okay.
So the first 2 weeks, I don't even take any penalty off.
Oh, okay.
Yeah. So, yay. The rest of the time, I typically take off a -1% per day. Okay. And so that is sort of it builds up, so don't let it like slide. But